Hi everyone, I am Muhammed Ustameroğlu. I will present a theoretical study of hyper self-attention through the lens of instructions. This is a joint work with Guanan Chu. We will focus on the seminal paper that is Attention is All You Need, which introduced the transformer architecture for machine translation. The core component of transformer is self-attention block, which led authors to name the paper as attention is all you need. So they emphasize the importance of self-attention. However, since the introduction of this paper, the transformers used and they became cornerstone of various domains. One application is the language modeling, where transformers excel at learning and understanding language patterns. In computer vision transformers have been gradually replacing convolutional neural networks in tasks such as image classification, object detection, etc. In reinforcement learning, we have decision transformers. Even the recent Nobel-winning advancements in protein folding utilize the transformer blocks for predicting the protein structures. What we see is even the transformers are so popular that people start to make their hardware more efficient for transformer block calculations. But why are they so good? I mean, what makes them so good that they are capturing all the deep learning applications, but no other architecture such as convolutions or recurrent neural networks do the same thing? Actually, people worked on similar questions. They theoretically and mathematically focused on transformers representation capabilities and the training dynamics. For example, they showed that transformers are Turing complete, or they showed that transformers can represent some image classification tasks and the gradient descent on that task converges to zero error. However, they focus on isolated problems. For example, in the image classification problem, they showed a mathematical and rigorous theory to demystify how transformers are good at vision. However, their theories does not say anything about the tasks such as reinforcement learning or natural language processing or protein structure prediction. Similarly, there are some other works on different problems, but they do not have a theory with a unified perspective across domains, which also explains the versatility of the transformers. However, I'll share a theory with you today that has a unified perspective. Generally, their convergence proofs depends on some assumptions about the parameters they are trying to show that converges or show something interesting about them. For example, they assume some parameters are lower bounded or upper bounded by some scalar, let's say, and they show that those parameters converges to something with that assumption, and that is not pretty. Contrarily, in our theories, we will not have such assumptions. Our assumptions will be only about the data distribution, and you will see that they are pretty mild. I mean, generalization is maybe more important to claim that neural network is actually learning something. Yet, to our knowledge, simply none of these earlier rigorous mathematical approaches has some generalization analysis. But I'll provide both test and out of distribution generalization analysis theories for you. As a last thing, those rigorous mathematical approaches does not have a clear interpretation of the parameters. They generally interpret only the attention maps, but we will have a clear understanding of the parameters. With that, the overreaching goal of this work is offering a unifying theoretical perspective on transformers through the lens of interacting entities. In particular, we will demonstrate that the transformers are mutual interaction learners. To show that, I'll first cover some background and explain our minimalistic setting, then I'll cover some necessary things to support our claim. Later, I'll briefly go over some null extensions to transformers, especially self-attention. This is the overall transformer architecture used in the Attention is All You Need paper that is designed specifically for machine translation. And when I say transformers are used in various domains, I mean this transformer block is used in various domains. To keep things general, of course, I'll focus on this transformer block instead of the specific architecture for machine translation. However, this block has some variations too, in terms of those layer normalizations and the feed-forward layers. Further, when we look at this block, the normalization layer and feed-forward layers are not novel, or they are not specific to the transformer block. They are seen in every other domain. The most crucial, the most novel and defining part about this block is this attention block is here. It is written as multi-attention, but it's called as self-attention too. Therefore, to both make our results to generalize to any domain and simplify a very hard analysis, we will focus on self-attention block. So let's look at what self-attention block is. You can think of its input as the X matrix you see here as a sequence of L entities. All of them are embedded into a d-dimensional vector space. We multiply each entity by these parameter matrices WQ, WK, and WV and get 3 different vectors for each entity, denoted and named as Q for queries, K for case, and V for values. The output of the model will be another L by D matrix, and each row of that matrix corresponds to one of the input entities. Now, let's step by step look at how the output corresponding to the first entity, that is x1 here, is calculated. First, you take inner product between each key with the first query, q1. Then you get as scalars, which is a vector of length L. Then you pass that vector through a general nonlinearity, which is generally like the sigma function you see here. People generally used row-wise softmax operation here, but we'll come to that. And you get another L-dimensional vector. Later, each of these entries are multiplied by the corresponding value vectors, and summing them, you get the output corresponding to the first entity. And you do the same thing for all entities in the input. And all of these operations can be expressed with this simple formula you see here. And the matrix inside this sigma function is called attention score matrix. And there's a 1 over square root of dk here. You can totally ignore it. It is just about some, better performance in experiments. It is just there for better optimization, so you can totally ignore it. We can just combine query and key matrices into another matrix. Let's call it C, and the same equation can be written like what you see at the bottom. Now, returning to the sigma function, recent papers have explored alternative sigma functions beyond the traditional softmax, such as linear, ReLU, cosine, polynomial, etc. They are shown to be competitive or even superior in some tasks compared to traditional softmax. So we see there's a variations in terms of this sigma function in the literature. To simplify the theoretical analysis and explain a diverse range of self-attention implementations, we look at linear variant of self-attention. That is the formula you see above. That preserves the core characteristics of self-attention variance through its dependence on the attention scores. That is the XC, X transpose you see here. Although omitting the sigma operation may appear to be oversimplification, extensive theoretical and empirical studies confirm the power of linear variant. For instance, layers of linear self-attention can implement gradient descent or preconditioned gradient descent, even functional gradient descent on some tasks in context. And there are some other examples too. Shortly, it is still strong and people showed it with experiments. Furthermore, an earlier work demonstrated that it replicates some key optimization dynamics of transformers. In short, this is a great model for our theoretical investigations, and in the following sections, we will focus on linear variant of self-attention. Now we'll continue with interacting entities perspective with the mutual interactions. We consider a discrete finite domain S. Here, what I call as domain is just an abstraction of several other possible experimental settings. We will come to the examples soon. In our task, we have tuples from this domain, possibly with repeated elements. These tuples are represented with the X you see here. And more abstractly, we can write it like this. We denote the length of the tuple with capital letter L. For each element in the tuple, we have a corresponding label element from another domain S sub y. So we write the corresponding label tuple, what you see here. Also, we say that these xy tuples are distributed according to a task distribution d of xy. And to feed these tuples into a neural network, we need to embed them into a vector space. So we have embedding functions for the domain S, and we have a corresponding function for the label domain too. With these definitions, I can now share the key equation for our theories. We look at the labels generated according to this aggregate mutual interaction function. In this expression, the f function you see here represents how much does jth entity has influence on the ith entity, which is a scalar. The bold w you see represents how does it influence. And summing over all the entities, we see the aggregate influence of all the other agents on ith agent. We believe that this is the most fundamental equation that the self-attention captures and the equation that explains self-attention. Let me give you two simple examples of mutual interactions, but if you're interested, there are even more complex versions of the same explanation examples and more complex examples in the corresponding paper. In many models, a DNA is composed of sequence of alleles, which we take as our tuple here. Some alleles are always active, others' activation level depends on the presence of certain alleles, and some remain inactive regardless of the context. And in a simplistic setting, we can write activeness levels of an allele as this function you see here. Here, p of xi captures the activeness of gene at position I. With plain English, the task here is representing the activeness of some alleles by looking at the DNA sequence, and this is an example of mutual interaction. Another example is the colliding agents environment. Let's say we have L-identical agents that move on a two-dimensional surface. They are identical in the sense that their policy is identical to. The policy is the algorithm that governs how the agents move, and it is identical to. We can denote each agent's initial position as the RFI vector, and we say if two agents collide, they get a minus reward. And we name the summation of all the future rewards as the value function of agent, which is denoted as V of RFI. If we look at the effect of jth agent on ith agent's value function, we can write it like this. Here, the f function is written in terms of the difference of the positions because the system we have is translational and rotational invariant. And we have w as a scalar in this case because the value function is a scalar. If we sum over the effects of all the agents on ith agent, we can write the value function of ith agent as this expression. With simple English, here the task is given the initial positions, predict the value functions of the agents. But for now, we keep this example as kind of incomplete. We will return to this when we validate our theories with some experiments. So let's for now just continue. Now returning to the big picture, here the equations you see are the genotype-phenotype task and colliding agents tasks we just see. But in the paper we have more details about them, but more importantly in the paper we have other different examples too, like time series prediction task or vision tasks. And all of these equations may look like different. All of these examples may look like different because their domains are different. However, in essence, they are very similar because all of them are mutual interactions. That means For all of these examples, you can find a specific f function and w vectors such that they are written in terms of this aggregate mutual interaction function you see here. With that, we can now explain the theories for our claim, that is, linear self-attention captures mutual interaction. Let's start with the representation. If the embedding dimension is equal to domain size, a single layer linear self-attention can represent these aggregate pairwise interaction functions for all entities simultaneously exactly with zero error. So one may ask, why do we look at the equal dictionary size? I mean, it may be impractical, right? For large vocabularies, it is definitely impractical. We analyze this case because it simplifies our analysis without changing the core insights. We can see how much self-attention captures the pairwise interactions without any distraction. And reducing D to be less than cardinality only introduces a small approximation gap without changing the core theory. Therefore, this is perpendicular to our discussion. So for now, we'll look at this version, but for completeness in the paper we provide a similar representation theorem by bounding the error in terms of some singular values of some matrices. Returning to the theory, when we say embedding dimension is equal to domain embedding size, self-attention can represent mutual interaction functions with zero error exactly. Consequently, self-attention can represent any of these examples we had. In addition to that, we need to have D greater than or equal to domain size for exact representation of any mutual interaction functions. Otherwise, we would get an approximation, as I said. However, if you let the number of parameters to be very large, generally any neural network can represent any function. So we need to compare things in terms of number of parameters. Therefore, let's compare self-attention with fully connected networks to see, one of the many reasons why we call self-attention is a mutual interaction learner, but MLP is not. From this theory, it is not hard to see that self-attention requires order domain size square parameters to exact representation of mutual interaction function. In the paper, we have another theorem that shows that MLP requires at least order L square times domain size square parameters for exact representation. So simply we see that self-attention is better at representing mutual interactions. Now let's look at more reasons why we say self-attention is a mutual interaction learner with our learning theories. But before that, let me explain a standard setting. We have input X and output Y matrices, and they are from a PXY distribution, which depends on our task distribution and the embedding functions. In our training data, we have Xn, Yn samples. We have B of B such samples that are sampled from PXY distribution, but with specific L star. That is, in our training data set, all of our tuples has the same sequence length L star. The objective is minimizing the mean squared error between self-attention output and the correct labels. And what you see here is pretty standard setting, nothing is special here. Before showing the learning theories, let me lay down our mild assumptions for the theories. We will first look at the data versatility assumption over a simplified example scenario where the domain has 6 elements and the sequences are of length 5. We define a count vector S of n. Each entry of the vector is a count of corresponding element from the dictionary in the sample X of n. For example, we do not have any apple in our X of n example here, so the first entry of S of n is 0. But we have 1 grapes, so the corresponding entry is 1. Similarly, we have 1 pear, so the third entry is 1. And we have 3 watermelons, and the corresponding entry, the last entry is 3. We also define a data matrix for each element in our domain. Its rows are count vectors such that we only pick the count vectors for which the count corresponding to the specific element is non-zero. For example, in the data matrix for watermelon, we have the rows from those count vectors, but we include those count vectors whose last entity is non-zero. Now our assumption is that for any such element from the training data, the data matrix is full column rank. I mean, this is very intuitive, right? To learn how entities interact, you need to see different configurations of them, such that different samples in this Sn vector you see is versatile. Actually, we proved that this assumption is satisfied with high probability if the covariance matrix of S of n is positive definite and the data samples are independent. For example, if each entity in the X tuples are sampled uniformly from the domain, for instance, for the first entity, you see here watermelon, we sample it uniformly from all the elements in the domain. We do the same thing independently for all the other entities. It is not hard to show that the covariance matrix of S of n is positive definite. So this requirement for our proof is satisfied. So this assumption, data versatility assumption, is satisfied with high probability. But we kept this version because this version is more intuitive and it captures the essence, that is to learn how things interact, you should see their different configurations. Our second assumption is realizability, that is self-attention can represent task. Seeing that we already proved that self-attention can represent mutual interactions, we can reduce this assumption to that task is mutual interaction. With that, we can look at our learning theories. The first part of our learning theory is convergence. If we choose the embedding dimension to be equal to domain size, and if our task is predicting a scalar label, and if we choose initial C matrix as 0 and initial WV as such that its entries in the domain embedding base are non-zero, then gradient flow in mean squared error converges to zero error. And here's the brief sketch of a very long proof. We simply define d of n vectors as the difference between self-attention prediction and the labels. Then we stack all these d of n's and define a large d vector. Then with some linear algebra, we showed that time derivative of this d vector is equal to minus an f matrix times d vector itself. Then with even more linear algebra, we show that this f matrix is positive definite, strictly positive definite in a subspace of the large vector space, and we show that this d vector stays within that subspace through all training. Therefore, coupling the results of step 2 and step 1, we can see that d converges to 0. Consequently, self-attention outputs converges to task labels. However, zero training error is not enough to guarantee we are actually learning something meaningful. So that brings us to our generalization theories. Under the same assumptions, if we let embedding dimension to be equal to domain embedding size, then the parameters achieving zero training error also achieves zero test error over the population. So it's a perfect generalization to new examples from the same distribution that it didn't see during training. On top of that, we have length generalization. Remember, in our training data, all of our samples were from a distribution with a specific tuple length L star. So although the training samples has the same number of elements in them, same number of entities in them, it is guaranteed that the parameters we get from training generalizes to different sequence length too. With this, we are done with our learning theories. But before moving to experiments, I'll state a corollary of the generalization theory proof. It will be useful when we try to interpret the learned parameters. This seems complicated, but again, I can describe it with a plain English. Let's say you have two different sets of parameters for self-attention that are functionally equivalent. Although the parameters are different, they lead to the same self-attention outputs. Under specific transformations to both sets, you will get a specific matrix for each of them, and those two matrices will be equal to each other as long as those sets of parameters lead to functionally equivalent self-attentions. I'll return to use of this when we look at the interpretation of the learned parameters. Okay, with all these theoretical results, I just showed that single layer self-attention can capture mutual interactions, but let's see if I really fulfilled what I promised at the beginning. First, I promised a unified perspective, and you got it with the mutual interaction tasks. I promised that our assumption for learning are mild, and they were simply that dataset is versatile, which is improved with high probability. And the other one was self-attention can represent a task. Again, we showed it with our representation theorem. Further, we claimed that our learning analysis includes generalization too, for which I provided two theories. As for the clear understanding of the parameters, let's first confirm our theories with a simple experiment, then show how we make sense of the parameters we get from the training. Think of L identical agents on a grid of size n by n. Their initial positions are denoted with R of I. Just to make the story easier, we say our grid is looped in the y-axis, so it is a cylinder. However, we do not have to do that. We are just doing it to simplify the explanations here. Each agent is modeled as a circle of radius r, and they execute a simple move right policy. Again, we choose this simple policy for easing the description here, but you do not have to make this selection. You can choose more complex policies too. It does not change the theory. The goal is to predict each agent's total future reward from the initial positions. Under this setting, if we think carefully, the final value function for each agent can be written with this expression. If the distance between the y coordinates is less than or equal to 2r, then the agent gets a -2 reward because they collide. As the embedding, we use sinusoidal embedding because it is similar to what people use in the large literature of positional encodings for transformers. For a specific domain size and radius, we derive these parameters that universally generalize to any length. Here WV is just a vector whose first index is -√2 and the rest are 0. And C is diagonal with entries from a sinc function. And C matrix as a whole looks like this. For our training distribution, we choose L star to be 20. That is, there are 20 agents. We sample 100k samples. After training, we reach 0 training and test error, even 0 error in samples with different number of agents. So with this example, we just validated our representation, convergence, test and out of distribution generalization theories. However, the learned parameters, as you see here, does not look like the ones we devised. I mean, the devised parameters are diagonal as you see, but the learned parameters aren't near diagonal at all. But remember our corollary, that is, if two sets of parameters are functionally equivalent, they will look like similar after a transformation, after a non-naive transformation, but they may look like different before that transformation. And after that transformation, you see both devised and learned parameters lead to the same matrix. And that means they are functionally equivalent. Okay, we just validated the theories with a simple example. But after all, we come up with all these theories and explanations so people in the future can use them to come up with other theories or some practical applications of them. But don't worry, for you we have practical applications too. We have two null extensions of self-attention that naturally arise from our theories. Now let's look at the first one. This was our mutual interaction function, and we said that it covers several mutual interaction tasks from various domains. However, if our task includes interactions like this, suppose agent I gets rewards only I is allied with J and K, but J and K does not form an alliance. Clearly this is not a mutual interaction, and the mutual interaction function we have cannot capture this. Thus, we are not guaranteed that traditional self-attention can capture this kind of interactions. Particularly, this is a three-way interaction, and we can write it as an example of this function you see at the bottom. And that function is a summation over all the possible interactions you see. That brings us to our hyperattention module, which is designed for capturing higher order interactions. It has some higher order tensors, therefore I'll switch our notation to summations. The same as self-attention equation can be written with this expression you see here. Similar to that, we write linear hyperattention of order 3 as you see here. You see it is similar with the self-attention, right? I mean, it has the same parameters C and WV, but they are three-dimensional tensors instead of two-dimensional metrics. Also, you see some more additional X inputs inside this expression to capture higher order interactions. And with similar representation and convergence theories and some example scenarios, in the paper we showed that hyperattention is a higher order interaction learner. And of course there are several details that you should take into account when you use them in your experiments, which will make it more efficient and scalable. The other novel module is specialized to capturing coupled feature interactions. We call it hyperfeature attention. It has its own story, which I'll not explain here, but I'll share its experimental results in case those results hypes you into this model. We ran several experiments and compared hyperattention, hyperfeature attention, and the self-attention based neural networks. Here the task is predicting the next token in an OpenWeb test in the OpenWeb text dataset. The vertical axis you see here, perplexity, which is the same thing as cross entropy loss. You see there are some hyperattention and hyperfeature attention variants. As I stated earlier, there are some bells and whistles about these models and architectures. I didn't cover them, and you can think of these different curves as some variations over these different bells and whistles. Here, the important thing is the red curve, that is the curve corresponding to self-attention. And what we see is our models have smaller perplexity, so they are better than self-attention in next token prediction task. Here the all of the models has single layer, and all of the models has the same number of parameters except for the hyperattention 2 variants. Here it has slightly more number of parameters. We compared slightly larger 3-layer neural networks too. Again, we see that neural networks based on our models pretty much consistently show better performance compared to self-attention. And in these experiments, I choose most of the hyperparameters the same as GPT-2 paper, so I believe they slightly favor self-attention based network. Also, these were the first results I got, so I'm sure if I tune the things more, I'll get better results for my architectures. Furthermore, I'm currently running some experiments with larger models, like couple billion parameter models, and I see that things are scaling up. In short, we have some novel modules that naturally arise from our theories, and with experiments we show that those modules are better than self-attention based neural networks in next token prediction task. Again, there are several other cool explanations, examples about abilities of these novel modules. Also, like you can see the trade-offs and how to use them. They are explained in the paper. A feature work of our paper is large-scale couple of billion parameter experiments with composite self-attention, hyperattention, hyperfeature attention network on domains such as natural language processing, reinforcement learning, and computer vision. Another feature work is investigating the theories where we do not choose embedding dimension to be equal to domain size. Lastly, our theories were for linear self-attention. In the future, one can come up with similar theories for several alternative sigma functions or for a general sigma function. In conclusion, we first motivated a minimalistic setting. Later, we defined mutual interaction that covers several domains such as genotype, phenotype, multi-agent reinforcement learning, computer vision. So our theory is based on a unified perspective. Then we showed that self-attention can represent mutual interactions, gradient flow converges to zero training error, and unusual to the literature, we had test and out of distribution generalization theories too. Also in our theories, we simply assumed that training data is versatile and nothing more. Later, we validated these theories with a simple experiment and provided a clear understanding of the parameters. And all of these provide a unified perspective to the question that why transformers are so good and versatile that we see them in every domain. Later, we investigated what self-attention cannot capture, such as higher order interactions, and we proposed some null extensions to those instructions, and showed that in next token prediction task, the networks with R models perform better compared to the self-attention based networks. This is the end of the presentation. Thank you for your interest, and of course you can find much more details in the corresponding paper.